Hello and welcome to this Zenotech webinar on the industrialization of high-order CFD methods. I'd like to start by giving a brief introduction to Zenotech. We're a team of computational engineering software developers based in the Bristol and Bath Science Park, and we have over 8 years of experience in the development of computational engineering software and the use of HPC. We have two software products, the first being ZCFD, which is a compressible finite volume solver. It is able to run on arbitrary polyhedral grids, and it also is able to make use of the latest state-of-the-art many core hardware that's currently available, such as GPUs. We also have the Epic product, which is a portal to cloud-based HPC. Therefore, it allows users to access HPC from numerous providers, and it can be accessed on a pay-as-you-use model. Therefore, it limits the amount of capital expenditure required to run large simulations. So on to the topic of this webinar, which is industrialization of high-order CFD. It's been shown that high-order flux reconstruction can be very useful when trying to perform high-fidelity CFD, for example LES and DES and simulations such as that. So here we have a couple of examples, which is the flow behind a nose landing gear, and here we can see some acoustic waves. And then on the right hand side we can see some turbulent flow behind a turbine cascade. So the high order flux reconstruction method has been demonstrated to be very good at simulating these types of flows, and the PyFR code, which was developed by Dr. Peter Vincent and his team at Imperial College, has been used for these simulations. So the Hyperflux Project was set up to try to bring this state-of-the-art technology to industry, and it has been done through the implementation of this method within a commercial software code, which was ZCFD in this case. We've tried to focus on making the use of the method as simple as possible for those who are more familiar with standard second-order finite volume techniques. So just to give an example of the benefits of high-order methods, here we can see a very simple flow case, which is the laminar flow between two parallel plates, and this has been run with the steady-state solver within ZCFD, the steady-state high-order solver within ZCFD, and it's also been run with an implicit flow solver. As we can see, we have a very coarse grid. We've only got 4 cells across the domain, and on the left-hand side we can see some solutions. So the black curve is the analytical solution, which we can't see very well here because it's been covered by the red curve. But the green curve is a solution where a linear polynomial has been used to define the flow within the cells. The blue curve represents a quadratic solution within the cells, and the red curve indicates a cubic solution within the cells. And as we can see, as we increase the polynomial order, we get closer and closer to the analytical solution. Therefore, high-order methods provide us the opportunity to have highly accurate simulations with relatively coarse grids. And ultimately, what we're trying to achieve is a highly accurate solution with the minimum number of degrees of freedom possible. So in order to make these high-order methods easier to use for industry, we have tried to aim to minimise disruption to current workflows. A particular issue with high-order methods is the development of high-order grids, in that if we're generating a coarse mesh, then typically we would want to use curved elements near the wall boundary to resolve the actual geometry. However, generating curved meshes is problematic and is an active area of research. Therefore, to try and minimise the disruption to current workflows, we've aimed to try and use standard CFD grids wherever possible. And when we detect that we're near a wall, the idea is to use a zonal approach where we would switch to more conventional finite volume techniques near the wall. Therefore, we can also use things like conventional RANS modelling or URANS modelling near the wall, which also allows us to achieve higher Reynolds numbers with these high-order methods. Where we're more interested in complex flow physics, we're then able to switch to high-order methods, and we can choose whatever polynomial order we want to use to represent the flow in those those regions. But a key requirement in all of this is that we must make high-order simulations affordable. So the high-order flux reconstruction method has been added to ZCFD. The solver is currently able to solve the 3D Euler and Navier-Stokes equations. It has an LAS subgrid scale model, and for RANS modelling has the Mentor SST model. We can run with known cell types up to 4th order polynomial bases, and we can run simulations which are steady state and time accurate. In order to achieve time accurate simulations, we've opted to use a dual time stepping approach. The idea being that if we're able to develop a fast steady state solver, then we can use the fast steady state solver with a dual time stepping scheme, which will allow us to run time accurate simulations where the time steps are chosen based on flow physics rather than numerical stability. So the convergence acceleration techniques which we've implemented within ZCFD are local time stepping, low Mach number preconditioning for when we're dealing with low speed flows, a technique called polynomial multigrid, and we're able to use explicit or implicit time stepping. The solver will run on many core architectures such as GPUs, and we're able to run across multiple GPUs or multiple CPUs using MPI. The output is in a high order paraview format. So now I'd like to just give a few more details on some of the convergence acceleration techniques, and in particular polynomial multigrid, which can be considered to be similar in concept to that of geometric multigrid. However, we only have one mesh, which is as coarse a mesh as possible. The size of the cells within the computational mesh are usually determined by the highest order polynomial that we're using for the simulation. So the solution is marched with a V-cycle, so we start off with the highest order, and we march the solution in time at the highest order, and then we restrict the solution to a lower level, add some forcing terms, and so on until we get to the lowest level. Once we're at this lowest level, we can then prolongate these corrections back up until we finally get to the highest polynomial order. And this is a very similar concept to that that's used for geometric multigrid. The reason that we want to try and use this sweeping essentially through the polynomial levels is that, well, first of all, when we're using lower order polynomials, there's less work to do, and so the simulations are a lot faster. But also the time step that's used for explicit time stepping, for example, is limited by the polynomial order as well as the wave speeds and the mesh dimensions. Therefore, if we have a lower polynomial order, we're able to take a larger time step, and therefore by doing these V cycles, we're able to march the solution in time a lot faster than if we just kept the solution at the highest polynomial level. So an example of this, of the benefits of this, can be seen in this video here. So here we can see the initial transient disturbance, which occurs when the cylinder suddenly appears in a uniform flow. And so on the left we see the case where we do not have polynomial multigrid, and then on the right we have the case with polynomial multigrid. And as we can see, with the polynomial multigrid, the effect of the disturbance is transmitted throughout the domain a lot faster than when we don't have the polynomial multigrid convergence acceleration. So the benefits of those can be seen in terms of the convergence curves. So here we have just a simple case of a laminar flat plate. And so if we look at the purple curve, which is an explicit solver without preconditioning, we can compare that with the light blue curve, which again is the explicit solver but with polynomial multigrid. And as can be seen, we've gained almost a factor of 4 in the reduction of the number of iterations required to use polynomial multigrid. And it should be noted that the cost of running polynomial multigrid per cycle is maybe a factor of 2 if we're with a polynomial level of 3. So we've also implemented implicit time stepping within ZCFD. And one of the issues we have with standard second order finite volume methods for implicit time stepping is that the Jacobian matrix which we have to deal with tends to be very dense in comparison to those for finite volume. Depending on the polynomials used within the cells, we can also end up with poor conditioned linear systems to solve, and it therefore just makes the simulation harder and harder to achieve. As a result, we've chosen a hybrid scheme, which is a lot easier to implement on many core hardware such as GPUs, and I'll just give a brief introduction to that. So we start off with the standard backward Euler time discretization, and this is the same as would be used with the finite volume methods. However, rather than keeping all of the information in the Jacobian on the left-hand side, we split the residual contributions from the cell we're dealing with and its neighbours. We then put all of the information to do with the neighbours on the right-hand side, and we use a symmetric Gauss-Seidel method to solve the linear system. The important thing to note here is that the Jacobian matrix which we have to deal with is block diagonal. It also doesn't have any terms to do with any neighbours, therefore we can treat each cell individually and treat each part of the Jacobian matrix individually. And by using the latest information from the neighbours, we're able to perform a sweeping iterative scheme, and ultimately we end up with our implicit solver. The benefits of the implicit solver can again be seen in the convergence curves for the laminar flat plate, and here we have the blue curve and the yellow curve, which are from the implicit solver. As we can see, there's been a fraction of the iterations required to drop the residual, almost 8 orders of magnitude. We get by far the best convergence with the preconditioned implicit solver. So in order to use these methods, we have a very simple diagram here showing the flow, the workflow within ZCFD. So we can take CFD mesh formats from a variety of sources. We can then choose which solver we wish to run, whether it's the second order finite volume solver or the high order solver, or a combination of the two. And the output from those solvers both will go into ParaView, and we can use a ParaView catalyst to monitor the simulations as they're progressing. And then finally we can export the data to a variety of formats, VTK, Insight, or a custom format should you require it. So just to show some examples of the solver, here we have the laminar unsteady flow over a cylinder. This has been run with the high order solver with a polynomial level of 2. The implicit solver has been used to solve each of the pseudo-steady state problems within the Joule time stepping scheme. And as you can see, with our relatively coarse grid, we are still able to track the structures being shed from the cylinder downstream. And again, here we have the unsteady flow behind the cylinder for the laminar flow case. However, this time we've used cubic polynomials within the elements, and as you can see, the structures are a lot crisper as we go up the polynomial levels. We've also applied the high order solver to more complex test cases. So here we have the unsteady flow around some buildings. This was again run with the high order solver with cubic polynomials within the cells, and it was a viscous flow solution using the explicit solver with polynomial multigrid convergence acceleration. And then finally, increasing the geometric complexity, here we have the DARPA sub-off model, which again was run with the high order solver with cubic polynomials, and again it was run viscous with the polynomial multigrid option. So just to conclude then, the high order flux reconstruction approach has been implemented within ZCFD, and we've validated it on a series of canonical test cases. The method implemented is based on the technologies that were developed for PyFR by Imperial College London. The development of the ZCFD solver has focused mainly on convergence acceleration with the aim of using an efficient steady state solver to be able to run unsteady simulations with the dual time stepping scheme. We have also tried to focus on allowing the solver to be used with standard industrial workflows, and we've focused mainly on trying to develop a zonal solver which will allow lower fidelity modelling near walls and high fidelity modelling where we require it. The project has also supported further development and validation of PyFR and its application to very large scale problems. And it's been an excellent collaboration between the Hyperflux partners, which have been Imperial College London, Zenotech and CFMS, and we found that the open innovation model that has been used has proved highly successful. For further information on PyFR, you can visit www.pyfr.org. For further information on ZCFD, you can visit www.zenotech.com. And if you have an interest in cloud-based high-performance computing, then please visit epic.zenotech.com. Finally, we'd just like to thank our project partners, which were CFMS and Imperial College London, and thanks also to Innovate UK and EPSRC.